Okay, this is our final lesson of Unit 3. It's 3.7, Applications of Exponential Equations. Exponential relations are modeled by the exponential equation y equals ab to the exponent x. 4 letters here. X and y are common letters. We're used to seeing those letters, but a and b are not necessarily. A in exponential growth and decay is the initial value. It's like our starting amount. And B is the growth or decay factor. When the base is bigger than 1, so when B is greater than 1, this is an example of growth. And when B is between 0 and 1, it's an example of decay. So I'm going to show you how we can apply exponential growth and decay and how we can solve questions that involve exponential growth and decay. And then at the end, I'm going to show you how you could solve any of those examples in 3.6 without guessing and checking. So a city's population can be modeled by the equation P equals 1.4 bracket 1.0415 close bracket to the exponent t, where P represents the population in millions, T years after 1985. In which year did the population first exceed 3 million? Well, that would make us need to understand what the beginning population was, or what the starting population was. Well, I said that A was the initial value. The initial value A is the first number before the base with an exponent. So the number before the base without an exponent is right there. The base, B, is there. There's your x, and there's your y, and there's your equation. Y equals ab to the exponent x. Same letters. So the beginning population is the initial value. That's 1.4. But it's in million, so it's 1.4 million. And we want to know when this population exceeds 3 million. So we should understand that this population is growing because if you look at the base is a number over 1. And when base is greater than 1, we have growth. And how much over 1 tells you how much it's growing by. Well, our number is 1.0415. If we take the 1 away, we're 0.0415 over 1. As a percent, that would be 4.15%. So we're growing by 4.15%. If this number was less than 1, well, we'd subtract it from 1 and we'd see how much less than 1 it is, and however much less than 1 it is would be our decay rate, how much we're going down by. So we want to solve this question. Well, the equation we were given was population is 1.4 times 1.0415 to the exponent t. And it asked us what time is the population going to be 3 million. So when is the p going to be 3? So we're asked to solve this equation. Well, how do we do that? Well, we're not going to be making any common bases because our base is a decimal. So the best bet we have is to guess and check. So how do we do that? Well, we're going to guess some times that will give us a population of 3. So let's try some guesses. Our equation says 1.4 times 1.0415 to the exponent t. We're going to guess some t's. 1.4 times 1.0415 to the exponent. Let's try 10. 2.1. So we tried 10. We got 2.1. That's not 3. But it is bigger than 1.4, so we're going in the right direction. Let's try something bigger. Let's try 15. 15's 2.57. Let's call it 2.6. 15's 2.6. Getting closer. Let's try 20. 20 is 3.15. That's 3.2. That's too big. So we're going to go somewhere between 15 and 20. Let's do 18. 18, 2.9. When did the population first exceed 3 million? Well, that's not over 3 million, so we got to do the next one. 19. Aha. So 19 years later, we went over 3 million. So what's that mean? Well, that means t is equal to approximately 19 years after 1985. Because remember, it was years after 1985. So what year was that? Well, 1985 plus 19 would be 2004. And there's our guess and check method. And a completely acceptable method to solve this question. If you get this question on your test, you can solve it by doing guess and check. Or you'll be allowed to solve it using the method I'm going to show you on the back. Two special cases that you should probably add to your survival guide are doubling and half-life. Now I said all of the equations are going to look like y equals a b to the exponent of x, but doubling and half-life are a specific version of that equation. So we've got a equals a naught times 2, because it's doubling, to the exponent t over t. And half-life is a very similar equation. But it's over h. What do you notice? Well, it's doubling 2. Half-life, half. The base is either doubling the starting amount, a naught means initial amount, or we're halving the initial amount. Notice this time the exponent is not just a t, there's this per d and per h. What are d and h? Well, d and h are these specific things called either doubling time or half-life. So if the question tells you it takes 4 hours to double, that's the d. If it says it takes 2 hours to half, that's the h. So watch out for that extra part of an equation. I should give one of these a shot. I'm going to skip this logarithm stuff. I'm going to show you that at the end. Caffeine has a half-life of approximately 5 hours. Suppose you drink a cup of coffee that contains 200 milligrams of caffeine. How long will it take until there is less than 10 milligrams of caffeine left in your bloodstream? Well, since it said half-life, we're going to take the half-life equation from the last page. Half-life equation was a equals a naught 1/2, and use 0.5 instead of a half, t over h. So anywhere we were given numbers, we're going to be able to put those numbers into the equation. Well, we were given 5 hours of a half-life. We were given 10 milligrams of caffeine. We were given 200 milligrams of caffeine. Let's organize this information. One of those numbers is a starting amount, one of those numbers is a ending amount, and 5 hours. You gotta figure out where that goes. So suppose you drink a cup of coffee that contains 200 milligrams of caffeine. How long will it take until there's less than 10 left in your bloodstream? So that means we started at 200 and we went down to 10. The starting amount is the A naught. The ending amount is A. So we're going to start at 200 and end up at 10 by cutting the amount in half. So now we got to figure out what the 5 hours is. Well, it's either the time or the half-life. It's either T, time, or H, half-life. Caffeine has a half-life of 5 hours. So it's definitely a half-life. Now we're just trying to solve this equation. Well, how do we solve? Well, we could guess and check. That's the method we just came up with. Or we could use what we're about to learn called logarithms. So let's try guess and check first and see what we come up with. So we're going to plug in some t's until we get 10. So we've got 200 bracket 0.5 to the exponent something divided by 5. So let's try 10. 10 divided by 5. We get 50. So we try 10. And we got 50. We want to go down to 10, so we need a bigger number. Let's try 20. 20 gives us 12.5. Closer. Let's go, that was a big jump. Let's do a smaller jump. Let's try 22. 22 gives us less than 10. Okay, here we go. 22, 9.5. So it's definitely not 22. We'll just say less than 10. We want to be less than 10 milligrams. That is less than 10. Let's try 21 and see if that's any better. 21. 21 gives us more than 10. Okay, 10.9. So that means, therefore, T must equal 22 if we're going to the nearest hour. So it happens somewhere between 21 and 22 hours. So if we wanted to do a conclusion, we might say it would take more than 21 hours, but less than 22. And that would be our answer. Now, I'm going to teach you how to use logarithms to solve, and then we'll come back and actually get the fully correct answer for this one. If you're doing this question on a test, you would be allowed to guess and check and come to the nearest whole number, and that would be a perfectly acceptable answer. But I'm going to teach you logarithms too. So if we're trying to solve for an exponent, and we have something like a number equals a number to an exponent, and we want to know the exponent, we can do that by doing log on your calculator of whatever's on the left side, and divide it by log of our base. So I'm going to show you that. So if we want to solve for this exponent, x, we can do that by doing log of 5 divided by log of 1.06. So log of the number divided by log of the base. And in a calculator, that would give us log of 5 divided by log of 1.06. We get 27.6. Now, if I asked you to do this question, you might be guessing and checking for quite a while before you came up with 27.6. To show you it works, 1.06 to the exponent, 27.6 equals 4.994, which is pretty close to 5. So this log method will work every time. Let's try this one. Now our exponent's not just x, but if we do log of 25 and divide it by log of 0.97, the base, we get the exponent. The exponent here is 2x. So we don't quite get x, we get 2x. Well, let's see. Log 25 divided by log 0.97 equals negative 105.7. Oops, put an extra point in there. Negative 105.7 is 2x, but if we want just x, we gotta divide by 2. And we end up with negative 52. All right, that's logs. I'll leave this one for you to try. You can check your answers on the course website. Logging. Let's come back to this question. Now, if we wanted to solve this, how would we do it? Well, we're one step away from being able to use logs. We can't have a number here. We can't do log of 100 divided, or log of 10 divided by log of 200 times 0.5. It doesn't work that way. So if we want to use logs, we have to divide the 200 away. If we divide both sides by 200, we get 0.005 is equal to 0.5 to the exponent t over 5. And now we can do our log trick. So the exponent t over 5 would be equal to log of our answer divided by log of our base. And if we do log of 0.05, we divide it by log of our base, we get 4.322. And to get t by itself, we would bring that up and multiply. 5 times 4.322, which would give us 21.6. So guess and check got us 22. Logging gets us the exact answer, 21.6, which is exactly between 21 and 22 hours. So we were right. All right. That's it for Unit 3. At this point, we should be finalizing our survival guide to get ready for our unit test. If you give your practice questions a shot, any questions you have, make sure to ask. And let's get ready for that test.